Hello guys, today we will learn about radial and transversal velocity. So, let P be the position of moving particle at time t and r its position vector, then the resolved part of velocity at P along and perpendicular to the radius OP are called radius and transversal velocity. Here, as you can see in the figure, P is the position of the particle and r is the radius vector, u is the radial velocity and v is the transversal velocity as it is perpendicular to the radius vector. Now here we can see the proof. Now you can see in the figure p is the position of the particle, and as you can see, if we are learning about radial and transversal velocity, then here will come some parts of displacement, then only we can learn about the radial and transversal velocity. Okay, so as you can see, the particle is displaced from point P to Q. So here the angle is del theta by which it is displaced, and so here if we get the radius, so here we get the position, that is r plus del r and theta plus del theta. Okay, now we know that u is radial vector, the u, we know that the radial velocity is u, so it is equals to limit del t is tends to 0 displacement along OP in del t time upon del t. So displacement upon along OP along OP, as we can see, the displacement is PM. So we have written PM upon del t, that is equation number 1. In triangle OMQ, that is a right angle triangle, so del theta is cos del theta is equals to r plus pm upon r plus del r. Then pm is equals to r plus del r cos del theta minus r. So put this value of pm in equation number 1 and we get u is equals to limit del t tends to 0 r plus del r cos del theta minus r upon del t. Limit del t tends to 0 r plus del r 1 minus del theta square upon 2 factorial plus del theta upon 4 factorial whole power 4, and it is continuing. Okay, and minus r upon del theta. Okay, so here are the some points that we have to keep in mind, that cos del theta is equal to 1 minus del theta whole square upon 2 factorial plus del theta upon 4 factorial, and it continues. Similarly, sine del theta is equals to del theta minus del theta whole cube upon 3 factorial, and it continues the term. Okay, so as you know, del theta upon 2 factorial, del theta upon 4 factorial is very small value, so we can neglect higher power of del theta and only 1 is left. Okay, so we get limit del theta tends to 0 r plus del r minus r upon del theta, limit del theta tends to 0 del r upon del t is equals to dr upon dt. Okay, so here as you can see, so radial velocity is equals to u del r upon del t is equals to r dot. We can write that dr upon dt like that only. Now we know that v is transversal velocity. So v is equals to limit del t tends to 0 qm upon del t. It is equation number 2. Okay, as you can see in the figure, qm is the perpendicular velocity that is changing. Okay, so qm upon del t. By triangle omq, sine del theta is equal to qm upon r plus del r. Okay, so qm is equals to r plus del r sine del theta. Put this value in second equation and we get limit del t tends to 0 r plus del r sine del theta upon del t. Now the way that we have learned how to expand sine del theta, expand like that only and neglect the higher powers, and we get limit v is equals to limit del t tends to 0 r plus del r upon del t into del theta is equals to limit del t tends to 0 r del theta upon del t plus 0. So if del t tends to 0, then del theta tends to 0. And we get the answer. Okay, now v is equals to r del t upon del theta upon del t, that is r dot r theta dot. If resultant velocity of particle at p is v, if the resultant velocity of particle at p is v, which makes angle alpha with OP, then v is equals to r square plus r theta dot whole square root, and tan alpha is equals to r theta dot upon r is equals to r theta upon r d theta upon dr, that is equals to tan phi. So we have learned what is radial and transversal velocity and how to prove it. And now then my that ends the topic, and thank you.